For problem 7, we have two force body diagrams. This is what it looks like for the first mass, M1, and this is what it looks like for the second mass, M2. What's important about these force body diagrams, and the key to solving these types of problems, is that this Ft is the same as this Ft. It's one rope, so if there's one tension of some certain newtons on one side of the rope, the Ft here, it's going to be the same as the force of tension that's holding the block up over here. So these two force tensions are the same. Otherwise, we could create our normal force body diagram. This is on an inclined plane, m1g down. So you have m1g cosine theta, which is going into the plane, and m1g sine theta, which is over here. And then you have your force of friction. You know the block is moving this way because the problem says find the block speed when the second block has fallen 30 centimeters. So in order for this to fall 30 centimeters, this block has to move up this way. And so the force of friction is always opposing motion. So the force of friction is going to be this way. So let's write out our equation. First, we know that the force of friction is mu k m1g cosine theta. Remember, it's the weight that's going into the block. So it's not just m1g, it's m1g cosine theta. And you multiply by mu k. So the sum of the forces is mass times acceleration. There is some acceleration. We know this because we know that the second block has fallen. There's some motion, so this acceleration is not zero. It's something greater than zero. So let's plug in what we know. The forces is this force tension, which is going this way, minus the force of friction, which is going opposite of it, minus m1g sine theta, which is going opposite of it, is equal to mass 1 times acceleration. We could rearrange this to figure out what the force of tension is, which is this whole mess right here. You just move all this stuff to this side. Okay, keep this just right here. Let's move to the second block. The second block is a little bit easier because it only has this force of tension up and m2g down. So the sum of the forces is force tension pulling up minus m2g equals m2a, because the sum of the forces is mass times acceleration. We know that, again, this acceleration is the same as this acceleration, because if the block is moving down a certain acceleration, this block has to be moving up that same acceleration. They're connected by this tense rope. So they're going to be, the movement's accelerations are going to be mirroring each other. It's going to be the same. So we can rearrange this to get force of tension equals m2a plus m2g. You just move that to this side. So now the key is this force of tension and this force of tension are the same. So we can just move all of this stuff into this force of tension and say this equals that. And that's what I did down here. m1a plus fk plus m1g sine theta, just all the stuff here, equals m2a plus m2g, all the stuff here. You could rearrange it so you have the accelerations on one side and all this other mess on the other side. And then you solve for acceleration. So distribute out the a, you get m1 minus m2 equals this thing over here. You just divide by this and you get the acceleration. So that was the key. You first figure out the acceleration first. And then you use your normal kinematics equations to figure out the velocity. So we know the initial velocity was 0. It starts from rest. And we use this kinematics equation, v squared equals vo squared plus 2a delta x. It's fallen 0.3 meters, so this is 0.3. The 2a, this is the a that we figured out from down here, right? So we just plug that into here. And this vo squared initially is 0, so then you just solve for this v.